All right. Um, Hi, Hannah. It's finally time to get back into it, and now I'm alone, so I can actually speak, which is nice. Um, I had a pretty crazy day today. I went to the hospital, UT Southwestern, to because I had a volunteer orientation for the geriatrics department. It's just like a little thing to prevent delirium in older patients, and I remember you told me that you really wanted to go to UT Southwestern, and I did too, But the campus is pretty depressing, and I've been going to this campus for it's like 6 weeks now, ever since I started my lab there, new lab position. But like, oh man, like every day it's like, I want to go there less and less. Of course, the goal was always to go to Baylor. That's like, I think the dream. Just get away from Dallas. And the way we get there is through this. So let's continue. Let's continue studying these. Hopefully, I can actually finish some videos today.
Reduction.
Oh yeah, and this was annoying. Like it was lagging yesterday.
Bringing in our 3-carbon malonyl attached to that acyl carrier protein, popping off carbon, and a couple
I
of
hope it
reduction
doesn't like
steps.
lag.
And ultimately, we're going to get to something that has 16 carbons. Now,
Test,
every time you run this
test,
series of
test,
reactions, every time you add 2
test,
carbons,
test.
it's
Okay.
going to cost a couple of NADPH for those 2 reduction steps. So, from 8 carbons to 16 carbons, we added 4 2-carbon units. 4 2-carbon units times 2 NADPH gives us another 8 NADPH that we had to use for this process. And then we're going to steps, and that's going to cost us
Looks
a
like
couple
it's
of
not stuttering.
NADPH. And so now we have a 6-carbon unit attached
Yeah,
to
I
the
actually don't
acyl
like
carrier
look over
protein.
this again.
So if we're going to reduce this, something else has to be oxidized. And the
So what's the point of this? Fatty acid synthesis. Okay, we're making fatty acids. So why are
allyl
we making fatty
decarboxylate
acids?
so malonyl CoA is connected to the
We need to store CoA because CoA is useful for the Krebs cycle because it's the first step. And so we start with CoA, malonyl CoA. First steps.
ACP. We're going to that coenzyme A. And now we have malonyl stuck to the ACP. We have the acetyl unit shifted to the other part of the fatty acid synthase enzyme. So this is kind of what it looks like at the beginning. Here is malonyl attached to the acyl carrier protein. Here is the acetyl unit attached to another location on the enzyme. The idea is that we want to bring this acetyl unit down to the malonyl. We're going to connect it to the malonyl, and we're going to pop off carbon in the process. So we're going to lose this carbon.
So malonyl is this structure here with like the two carboxylic. Well, it's not an. This is an acid, carboxylic acid. This is I don't know. And then acetyl unit has elongation. We're making it longer.
As carbon dioxide. This action, connecting our 2-carbon guy to what used to be a 3-carbon guy, is going to be performed by yet a third party of the fatty acid synthase enzyme, referred to as the condensing enzyme. So, condensing our 2-carbon guy with our 3-carbon guy and losing one of the carbons in the process. At first, it seems a little counterintuitive. I mean, we just added this carbon and now we're removing the carbon. But this is kind of a common theme in biochemical pathways, in that the removal of a carbon can drive an unfavorable reaction.
This is what pentose phosphate pathway. Add a carbon, remove a carbon. Is this what this is?
Forward. This is a favorable reaction. so it can drive an unfavorable reaction, the joining of these two things, forward. We saw this with gluconeogenesis.
Oh, okay, okay, okay. Okay, pyruvate. Add a carbon. Do we remove it? Yeah, see? Okay. Adding a carbon, removing a carbon. And I'm guessing it's going to say to drive the reaction forward. It's a highly exergonic pyruvate kinase reaction, PEP to pyruvate. Wait. This is PEEP, phosphoenol pyruvate. How much of this we actually need to know, like, for a question? But I'm like pretty sure like it's important to know it anyway.
Our first step in gluconeogenesis was to carboxylate pyruvate, take our 3-carbon guy, and turn him into a 4-carbon oxaloacetate, and then immediately decarboxylate oxalose tate to phosphenol pyruvate, or PEP, another 3-carbon guy. So the addition of a carbon followed by the removal of a carbon to drive an unfavorable set of reactions forward. So now we have something that looks like this. We have brought our 2-carbon guy down and attached it to our 3-carbon guy, lost a carbon as carbon dioxide. So now we have a 4-carbon structure attached to our acyl carrier protein. And we have to do 2 reductions on this. We want to get rid of the oxygen, and then we want to reduce it even further to single bonds. So our first step, we're getting rid of that oxygen and creating a double bond. This is a reduction. We've lost the this, something else has to be oxidized. And the guy who's going to be oxidized in this case is NADPH. NADPH
Isn't
provides what we
NADPH the same thing that reduces? Oh no, this is oxidized. In the previous video we watched yesterday. Bro, this website is so slow, bro. I'll be right back. Aqua. Got my aqua.
The release.
Okay, so I was saying NADP plus is the one that is uh oxidizing oxidizing the step that removed the double bond or something. FAD removed the acetyl-CoA. Oh yeah, so you take NAD, you freaking you're removing, so it's reducing actually. Yeah, it's reducing this, and FAD2 plus is. Wait, honestly, I can't believe I forgot this already.
NADH going to add this bond here. We're going to move a couple of hydrogens and generate a double bond. So the enzyme we're going to use to do that is called a dehydrogenase. When you oxidize something, we're going to oxidize this bond here. You're going to have to reduce something else.
Removing the hydrogen
So
off.
the molecule that gets reduced is an FAD. We're going to create an FADH2 in this step, and a double bond here between these guys. And then in a couple of steps, we're going to do another oxidation, this time on this carbon, essentially attaching an oxygen here, much like our double-blinded oxygen here.
So in this situation, NADPH is this is this being oxidized because we're losing a hydrogen.
We say what we call the reducing power for this reaction. NADPH is generated by a carbohydrate metabolic pathway called the pyruvate, called the pentose phosphate pathway. So this is a product of the pentose phosphate pathway. He's going to be oxidized. In the process, our fatty...
What did I say? I said this is reduced. Yeah, because this is donating a hydrogen, so it's being reduced.
Then we have to do one more reduction step to get rid of that double bond, and we end up with a single bond still attached to the acyl carrier protein. And since this is another reduction, we're going to require another NADPH to get oxidized.
That's what
so a total of 2 NADPH to reduce this double-bonded oxygen down to a series of single bonds here. And now we're just going to repeat that. We're going to shift
so NAD to add, NADPH to remove.
Or carbon guy to our fatty acid synthase to another portion on the enzyme. And we're going to bring in another malonyl ACP. So here is our 4-carbon guy attached, shifted to a different portion of the enzyme, and malonyl coming in into that acyl carrier protein site. And we're going to repeat it. We're going to get rid of carbon. We're going to connect to our 4-carbon unit here to this 2-carbon guy, and lose this carbon as carbon dioxide. And then we're going to do our 2 reduction steps, and that's going to cost us a couple of NADPH. And so now we have a 6-carbon unit attached to the acyl carrier protein. We're going to shift that up to the different side on the enzyme, bring in another malonyl, do a couple of reduction steps, and pop off a carbon.
Is that it? Did it?
Maybe the other way around, steps, and pop off a carbon. Or maybe the other way around. Pop off a carbon, do a couple of reduction steps, and now we have an 8-carbon guy stuck to acetyl carrier protein. And we're just going to keep repeating this, shifting it to a different side of the enzyme, bringing in our 3-carbon malonyl attached to that acyl carrier protein, popping off carbon, and a couple of reduction steps. And ultimately, we're going to get to something that has 16 carbons. Now, every time you run this series of reactions, every time you add 2 carbons, it's going to cost a couple of NADPH for those 2 reduction steps. So from 8 carbons to 16 carbons.
So you're just getting a lot of these and you're just adding that with NADPH. So you need pentose phosphate pathway to be fat.
16 carbons. We added 4 2-carbon units. 4 2-carbon units times 2 NADPH gives us another 8 NADPH that we had to use for this process.
Do we have to
and
keep
then
track
we're
of
going
this?
to shift this off to another site in the enzyme.
Is that like a
Pop it off as a free fatty acid. The maximum length of fatty acid that we generate using this process is 16 carbons. We can make longer fats, but we're going to use different enzymes to do that. Let's do a quick comparison between fatty acid synthesis and fatty acid oxidation. We know the locations are different. Fatty acid oxidation happens in the mitochondrial matrix.
Oh, okay, that's in between the two layers, right? Because mess this up. Okay. If it's inside the mitochondria, I'm actually okay. Good. I was right. It's inside this. Wait. Dang it. It's inside. Oh, it's an intermembrane. Oh, yeah. Okay, so what is it? What'd she say? She said pentose. She said oxidation. Fatty acid oxidation and mitochondrial matrix. Oxygen is breaking apart.
It initiates in the cytosol, but then gets shifted into the matrix for the actual oxidation steps. Fatty acid synthesis occurs in the cytosol, and often, opposite pathways will be found in different locations of the cell to keep the enzyme separate, so we don't run these as cycles at the same time. In fatty acid oxidation, the fat is initially
I
linked
think
to coenzyme
ETC is the
A.
only thing in the
In fatty acid
intermembrane space.
synthesis, we are initially linked to that acyl carrier protein. And then,
Honestly, I forgot the
step
ACP.
in fatty acid synthesis is to connect that acetyl-CoA to the fatty acid synthase subunits called amine. So malonyl-CoA is connected to the. We're going to get acetyl connected to AC. First enzyme is on one of its subunits called acyl carrier protein. Acyl carrier protein, or just ACP. So we're going to connect our acetyl-CoA to the ACP subunit of fatty acid synthase. We're going to get acetyl connected to ACP and a free coenzyme, A. Now we're going to take this acetyl unit and we're going to shift it to a different part of the fatty acid synthase enzyme. And then we're going to bring in our malonyl-CoA and attach it to that acyl carrier protein. So malonyl-CoA is connected to the ACP. We're going to, again, release that coenzyme A. And now we have malonyl stuck to the ACP. We have the acetyl unit shifted to the other part of the fatty acid synthase enzyme. So this is kind of what it looks like at the beginning. Here is malonyl attached to the acyl carrier protein. Here is the acetyl unit attached to another location on the enzyme. The idea is that we want to bring this acetyl unit down to the malonyl. We're going to connect it to the malonyl, and we're going to pop off carbon in the process. So we're going to lose this carbon as carbon dioxide. This action, connecting our 2-carbon guy to what used to be a 3-carbon guy, is going to be performed by yet a third party of the fatty acid. This
Sorry, I was
and we're going to
I was thinking about an old friend. Not the same one as yesterday, but
to the malonyl.
yeah.
We're going to connect it to the malonyl, and we're going to pop off carbon in the process.
Wait, what is
So we're going to
ACP
lose this
though?
is that we put it to the malonyl, and we're going
We
we
just
want
need
to
it.
the acid synthase enzyme. So this is kind of what it looks like at the beginning. Here is malonyl attached to the acyl carrier protein. Here is the acetyl unit attached to another location on the enzyme. The idea is that we want to bring this acetyl unit down to the malonyl. We're going to connect it to the malonyl, and we're going to pop off carbon in the process. Using this process is 16 carbons. We can make longer fats, but we're going to use different enzymes to do that. Let's do a quick comparison between fatty acid synthesis and fatty acid oxidation. We know the location. Opposite pathways will be found in different locations of the cell to keep the enzyme separate, so we don't run these as cycles at the same time. In fatty acid oxidation, the fat is initially linked to coenzyme A. In fatty acid synthesis, we are initially linked to that acyl carrier protein, and then a bunch of shifting occurs. Our coenzymes in fatty acid oxidation are NAD and FAD. Fatty acid oxidation means that we are
Is the
oxidizing the
reduced
fat, so
version.
something has to be reduced.
But in the synthesis, it's the reduced version. It's like the NADPH and FADH2.
And the guys who are going to be reduced are NAD and FAD to produce NADH
Oh, there's no
and
FAD.
FADH2.
Okay.
In fatty acid synthesis, we're going to
Wait,
have
did
to
she say that?
FADH2.
She
In
did.
fatty
She
acid
did.
synthesis, we're going to have to reduce the fat, and so something's going to have to be oxidized. The guy who gets oxidized is NADPH. He's going to be oxidized to NADP. In fatty acid oxidation, our goal is to generate
What'd she say about
the
him?
acid NADH. Guys who are going to be reduced are NAD and FAD to produce NADH and deoxidized fatty acid ATP to initiate the action. Our goal is to generate ATPized. The guy who gets oxidized is NADPH. He's going to be oxidized to NADP. In fatty acid oxidation, our goal is to generate ATP. Yes, we used a couple of ATP to initiate the process, but after that, it was pure energy generation. We generated FADH2 and NADH during the fatty acid oxidation cycle. We also created acetyl units that could be put into the Krebs cycle to generate even more FADH2 and NADH. And when all of those reduced electron carriers go through the electron transport chain, we're going to make a ton of ATP from that. Fatty acid synthesis is going to require ATP because remember, our malonal units are 3
We have too much ATP, we don't need it.
acetyl units, the cost of 1 ATP. So every time you generate a malonol, it's going to cost you an ATP. So lots of ATP is being used here, but that's okay because fatty acid synthesis is going to occur when we are rich in ATP when we have energy, and we want to store it as reduced fat molecules. Let's summarize what we talked about in this video. We discussed the details of fatty acid synthesis, DH.
So if I want to lose weight, I want to activate this and only this. I need to generate ATP, which is just working out. Goofy. Isn't that how that's so funny how that works? The problem is the system's not that simple. There's neuroscience, there's heavy neuroscience. That's what my lab is actually studying. That weight set point, obesity. Interesting.
During the fatty acid oxidation cycle, quats are being generated from our ATP when the details of fatty acid synthesis, where it happens in a specific process. And we did a comparison of fatty acid oxidation and fatty acid synthesis, including their location, the coenzymes needed, any energy needed, and what you're initially linked to.
I feel like location is a big point because I do remember some questions they ask about the location. Okay, let's ketogenesis. Go faster.
In this video, we'll be discussing ketogenesis. So, ketogenesis is what happens when you're in what's called a long-term starvation state. Now, we consider long-term starvation to be, maybe several days you haven't eaten, or several weeks. To your body, this is really a much shorter time frame. Basically, your body considers anything.
Don't tell me you're gonna lag now. Oh my gosh, I'm actually really tired. Should I say it? I'll say it another time. Wait, how long has it been? Should I just go to bed? Loki.
Greater than about 12 to 24 hours to be long-term starvation.
12 to 24? Wait, what?
Greater than about 12 to 24 hours to be long-term.
To be long-term starvation. So it kicks in. 12 to 24. Wait, what? It's been 24 minutes. I'll push.
Starvation.
I'll push a little
12
hard.
to 24 hours you can manage.
This sounds pretty interesting too, actually. It's all to do with hunger and weight gain, weight loss, fat. It's interesting. Okay, maybe this is a good tab. Maybe I should close this. Ask this to play it for me. If it will.
That's your typical overnight fast. You went to bed. And you woke up the next morning. And that was 12 hours, let's say, without food. And so, while you were sleeping, your body is breaking down glycogen. You typically have enough glycogen to manage about 12 to 24 hours. So if you continue to fast during that day, you'll probably still break down glycogen stores, and you'll be all right. But at the end of that 24 hours, now your body has depleted its glycogen stores, and now considers itself to be in long-term starvation. So, during this long-term starvation, obviously, your blood glucose levels are going to fall. And to meet energy demand, your body is going to shift to fat metabolism and start breaking down fats through fatty acid oxidation. So, your levels of acetylcholine are going to increase because fatty acid oxidation results in acetyl-CoA production, and then ultimately putting that acetyl-CoA into the Krebs cycle to generate NADH and FADH2. Some of that acetylcholine, of course, will feed into the Krebs cycle. But some of the acetyl-CoA may not be able to get into the Krebs cycle because the Krebs cycle might be overtaxed. It might be running as fast as it could. If you have a significant number of these acetyl-CoAs feeding into it, the enzymes are going to be saturated. Plus, if your blood glucose levels are low, then you're likely going to be doing a little gluconeogenesis. And recall that one of the starting materials for gluconeogenesis is oxaloacetate. So some of the oxaloacetate that might normally be participating in the Krebs cycle could be drawn off into gluconeogenesis. So you got tons of substrate for Krebs cycle, is overwhelmed, and may not be running super efficiently because oxaloacetate is being drawn off. So you may have some excess acetyl-CoA flowing around that really don't have anything to do. So these guys are going to react together to form what we call the ketone bodies. And this is ketogenesis, and the ketone bodies can easily travel in the bloodstream. And they can cross the blood-brain barrier and enter the brain and be reconverted to astro-CoA. And this is really your primary source of energy for the brain during starvation. The brain cannot do fatty acid breakdown, can't use fatty acids as fuels. It can really only use the acetyl-CoA, and it can use glucose. So if glucose is unavailable, it can get its acetyl-CoA from these ketone bodies that can travel around and enter the bloodstream. So let's take a look at this process, that a couple of the acetyl-CoAs. And they're going to join together to form a acetoacetate. Acetoacetate can be broken down, rearranged to form a couple of other ketone bodies called hydroxybutyrate and acetone. So these three structures, acetoacetate, hydroxybutyrate, and acetone, those are your ketone bodies. You should recognize these names for the MCAT as ketone bodies. And this all sounds well and good, except for the fact that these ketone bodies are acidic. So an accumulation of ketone bodies can lead to a drop in blood pH and a condition called ketoacidosis. This is not typically a problem in normal individuals. And by normal, I mean people who can metabolize glucose, because you're going to be doing a little gluconeogenesis, and so some glucose will be out there. And so it tends to balance itself out between ketone body formation and glucose levels, and both of those can be used as fuel. The problem comes when somebody is unable to use glucose as fuel, like a diabetic. Diabetics cannot take glucose out of the bloodstream because they either lack insulin or can't respond to insulin. As a consequence, glucose as an energy source is off the table. The only thing these folks can use is fats and proteins. And so there's a real excess of fatty acid oxidation in a diabetic individual, and so a real excess then of ketone body production, and potentially fatal ketoacidosis. The blood pH can shift so much that it can cause serious problems and be fatal. One way that you know that a diabetic is in ketoacidosis is they are breathing very rapidly to help restore normal blood pH. And their breath smells of acetone. Acetone is a very volatile compound, and so it can be exhaled. You might recognize acetone because we put it in paint removers. Paint removers, nail polish remover contains acetone, has that kind of sweetish smell. So if you have a diabetic who's really breathing rapidly and their breath smells of acetone, you know they're in some pretty dire straits, and they're going to need some help. Let's summarize what we talked about.
What do you do? It just says, "Oh, you need help." Okay, that's great. Let me call it. What do you do, man? Let me guess. You can't because it's an internal insulin problem. And you can't just administer insulin.
We reviewed ketogenesis and why that might happen. And we looked at the three main ketone bodies that are formed during ketogenesis.
Blood pH is terrifying, though. Okay. Protein catabolism. I should review these. ETC in one video? And fermentation? How less do we need to know? How little do we need to know? Okay, I'm tired. I'm going to wrap it up. I did my thing for today. See ya. Still miss you.